it's like 40 degrees, 45 degrees, in some places it's even touching 50 degrees. It becomes so difficult for the workers to actually be holding it in the first place.
True. You take a structure, you cut it and connect it. Now would the connection be stronger or the uncut structure be stronger? Like, I would love to empathize on the quality of product that you are making. It's in par with the European standards.
Focus right from day one was that when we got into it, that we want to create a world-class product, because
And every time a kid bruises himself with these rusted objects, they have to go take the kid and get a TT shot. And if I were to bend it, it comes back to its original shape. At the same time, if I were to show it using a steel rod, I can just bend the steel rod and the shape remains the same. Arguments are brought by people who are running the market, the material market.
So Dr. Srujan, 6 years of research in fiberglass composites, that's a very long period of time. I'm just curious, like, what were your top 2-3 findings about this particular material? What were some of the things that, like, we all have an hypothesis before we get into a research? Like, of course, you might be having some hypothesis. What were some of the things that really surprised you at the end of your research? So if you can just throw a bit of light on this, it would be great.
Of course, I mean, if I start talking, I'll probably take an hour just to speak about my 6 years of research. But, when I started, there's something called background study that we do. So I looked into close to around 40 to 50 published papers. And there's one thing that I found about this material, that it fails abruptly. Compared to steel, when you're putting steel on load, it has various phases on how it fails. So you have your elastic region, you have your elastoplastic region, and then you have your plastic region where you get your ultimate load. But for GFRP, at ultimate load, it would just snap. It would break.
So if we take the stress strain curve, what they say, so in steel, if it goes like this, here it would go like this.
Correct. So we don't have a curve for GFRP. For steel, it is a stress strain curve. But for GFRP, it's a straight line. Okay, so, and I was keen on looking into why this thing is failing abruptly. And imagine having something like this in a building wherein, some disaster happens and suddenly the entire thing collapses. So that was the thought in my head, and I came up with this concept called robustness. So not only did I want the structure to be strong, I wanted the structure to be robust, having that factor of safety, not just in design, but in actual execution. So while going through various code books, I did study the American code standards, the Euro code standards, the British code standards, the Australian, the Canadian, the Indian. I went through it all, right? I found this concept called structural fuse in Euro codes. So I wanted to implement structural fuse in GFRP. So at ultimate loading, you know how a fuse works, right? At maximum current, the fuse just breaks. So at ultimate load, I want this fuse to break, indicating that there can be chances of failure. And by then, everyone can evacuate from the structure at least, right? That was the basic thought process. But when I kept looking into it deeper and deeper and deeper, of course, initial 8 to 10 models that I developed were unfortunately not successful at all. I couldn't achieve anything. But that failure taught me so much that the next set of 10-15 models that I developed, more or less 40% of them turned out to be super strong. They were super robust, and they had the element of structural fuse. The curve was, the graph was no longer linear. The graph was curvier, just like steel.
Wow.
And that was a wow factor. And everyone were astonished. Because just using connections and mechanical properties, I engineered this to match that of steel.
Wow.
I engineered GFRP connection to match the graph of steel.
Wow.
Right. So
that sounds hard to believe, to be very honest, because we do meet a lot of the structural engineers, and every time they say this thing, but this material, it goes like this and it comes down like this. And of course, there are ways to kind of engineer it. But I think what you are sharing is really eye-opening, that by the research or the experiments, what you have done, that there is a way where the graph, which is one of the biggest limitations of this material, can be made into a curve. So really, really fascinated by the whole thing.
I can explain the curve also. There's something called yield point. There's something called ultimate load point when you're, testing steel under load. But for GFRP, there was only one ultimate load point. But my connection showed yield point as well as ultimate load point. Not only that, to a certain extent, it did have that elastic behavior. It did show plastic behavior. It did show that elastoplastic behavior also. And all this just by changing the way how the connection is made. So if I were to ask you, you take a structure, you cut it and connect it. Now, would the connection be stronger or the uncut structure be stronger?
Obviously, the uncut structure would be stronger.
That's the common answer I get as well. But in my case, my connection was 128% stronger than the uncut section.
Seriously, that is hard to digest.
It sure is, and I have a patent on it.
Wow.
And I was able to establish that connection after testing close to around 20 to 30 designs. Wow. And each design had about 5 to 6 samples made. So it was a lot of work. And while I was doing it in the UK, it was so difficult to find help because labor in UK is very expensive. Had it been in India, we could have gotten in a lot of people, a lot of fabricators, a lot of people who have worked with such material. Even for me to bolt something, right? Each connection had close to around 16 to 24 bolts in it. So there were bolted connections, there were bonded connections, there were hybrid connections, and there were composite connections. So these are the categories of connections that I have worked on. So even for me to get help and do all these models, it took me close to around 3 months just to do the models, the samples, the specimens. And testing took another 2 months. In fact, in my master's degree, I had to take an extension, a small extension, about a month's extension to submit my thesis. And the university happily granted it. Because in my batch, I was the only one who came up with a research paper. While all my peers, they were glad that their thesis was over. My curiosity was still there because there was so much untapped in this material. And if I were to go back, now I do guide a couple of students. And I do tell them and I show them certain things that are, decided during my master's itself. So the scope of further research, what I've written in my master's thesis, is the aims and objectives of my PhD thesis. And I was able to achieve all this when I was 22.
Wow.
So by 22, I had already figured out what I want to do my PhD in. And even today, when I address a lot of students, I tell them that it's very important to be decisive on earlier stages in your educational career on what you want to do further. Because just that little deviance, just that little preparations is going to take you a long way. And that's how I ended up doing my PhD.
Very, very interesting. In fact, I didn't know that there is so much to it, that there are so many different types of jointing mechanisms, that there is so much more to this material. And it's really, quite fascinated. And this is someone who sees this material every day, day in, day out. We have been kind of trying to educate the market. And so much learning from this particular interaction. So grateful for you to come and share. And I'm sure 6 years, we cannot kind of break it up into just an hour. But thank you for sharing those nuggets and those insights. So thank you so much on that. To be very honest, even I did not have that dead load can have so much impact in terms of One is, of course, creating more efficient structures, but at the same time, kind of ensuring that the costs angle as well. I think a lot of cost savings can also happen. So thank you so much for kind of shedding insights on that. And as you rightly said, it's across the entire spectrum, right from the manpower angle as well, that today, if you take workers, like when something is lightweight, it's so much easier for them.
Of course.
I think one thing that everybody in the construction industry would agree that the biggest challenges today is the workers' availability. And anything that will kind of cut down the time of completion by making it faster, more efficient, kind of a thing, will always have a very, very bright future. And I think that is one area where FGC can really play a good impact, particularly in the right now when we are in middle of summer, like the temperatures are so high. Now, thanks to global warming, like it's like 40 degrees, 45 degrees in some places, it's even touching 50 degrees. It becomes so difficult for the workers to actually be holding it in the first place.
True.
So I think even from an engineer's point of view, that when we are, or a contractor's point of view, that anything that we can do to make the life of the worker easy will lead to better retention and can yield a lot of benefits in terms of time to completion. And even from an end user's perspective, I think one thing like Indian construction industry is always like bad-mouthed about is that we never deliver on time. So I think anything that will kind of help us
curb down the time,
help us to finish our projects faster, I think there's definitely a big impact over there. Dr. Srujan, one very curious question. So you did your PhD quite some time back. At that point in time, there was so little awareness in India. How did you actually get your hands on the material in the first place to do your research?
My God, that was a struggle for me to get my hands on these things, because I saw that there were hardly anyone who was manufacturing this material. There were some people who were manufacturing it in Gujarat, Jamnagar, Surat, somewhere in that quarters. And they were only exporting it. So for me to get my hands on these things, it was very difficult. And I had to go back to my initial master's days, wherein the man who was supplying it to me from Europe, he started exporting it to India. And that's how I got my hands on these things initially. Then later when I found distributor in Gujarat, I directly sourced things from him. But other than that, I also faced a lot of backlash with respect to this material. When I was about to start my PhD journey, I obviously went and inquired and I asked a lot of professors and so on and so forth. The first thing that they asked was, how are you planning on getting this material? And even if you do get it, how much is it going to cost? And my answer would be roughly about, since I was importing it from Europe, my answer was like roughly about 4 to 5 times more than steel. Like, it's pathetic. Doing this entire research is pointless. In fact, there was this one man, he even accused me of saying, are you doing this only for the doctor title? Because if you are, you can be honest about this, because this material is not feasible. But deep inside me, I knew that this material is gonna be a star one day, just like your brand, Shine Star. And I was also curious to know that how did you get into manufacturing this material? Did you have any backlashes from friends, family, relatives saying, why are you getting into something new? Like, what gave you the confidence to start manufacturing this? So before getting into this, I just want to touch on that point, the kind of backlash you got on the cost aspect. That is almost 3-4 times. So actual FGC, the fiberglass composite, is 3 to 4 times more expensive when we see it on a kg basis. But because it's such a lightweight material, like we have this sample, now this section in square tube, if it were in steel, it'd be so heavy. Because it is 4 times lighter, it is actually quite competitive. And that's one of the biggest misconceptions, that people just dismiss it. Oh, the costs don't work out for this, so let us not explore it. But because of its lightweightness, and the scale of production also that it's happening, it's very, very affordable now. So I think there's a
big scope, because the entire market is moving towards more durable materials, not just like shifting to FGC, but even in steel, if we see like people are moving from MS to GI to aluminum and SS. So I think that's a trend that's going to happen, that everyone is going to move towards more durable, rust-free kind of a products, and FGC has a scope in that. In terms of other backlashes, what we have faced, nothing major per se from a manufacturing point of view, but in terms of an adoption point of view, we did face a lot of challenges. India still to some extent is a herd mentality market in terms of like, if everybody is using it, then I would kind of use it. And I think where we made that mistake initially was saying that it's a new material. Because the minute you say it's a new material, people are like, oh, it's an untested material.
Correct.
And the default setting in a human brain is to mitigate your risks. So I think that was where we kind of erred initially. And now our communication is always that it's not a new material. It's actually a very old material.
Very old, 100 years of history almost.
Exactly, almost 100 years old material. So that's the change in languaging that we are doing. And there is so much research that has been done on this. If somebody just goes on Google and just types out, there's like at least thousands of research papers done, so many applications, code books. So I think it's just that in India, like I'm sure this will catch on very fast. And like whenever I've traveled abroad, the world has transitioned to carbon fiber, which is like 10 times more expensive than this. So I think in the next 2-3 years, we'll have a very fast adoption of fiberglass composites, is my assumption.
We definitely will, and even I'm banking on it. And about the cost being based on weight, I was actually fed up of explaining that to people. I grew so impatient. I would just say, yeah, 4 times, 5 times. Like I wouldn't even explain that, no, I'm measuring it in meters, not in weight, not in kilos or pounds or whatever, because the material is 4 times lighter and all that. I'd just grown so impatient. And I think other than my family and my close set of friends, no one believed in me. They were like, oh, this guy is just doing something for the sake of doing that PhD degree and all that. But now that I see people like you coming into the market, and my God, and one more thing I wanted to tell you, I'm glad you're calling it FGC as a market differentiator. So I've literally worked with about 9 to 10 suppliers right now. And a couple of them have been from the European market. Like, I would love to empathize on the quality of product that you are making. It's in par with the European standards. And since there are so many players in Indian market today, and everyone's calling it GFRP, it's become a very generic term. So I'm actually glad that you're calling it FGC, so that there's a differentiator. And even when I was testing materials, right, initially, the steel that we're using today for structural design and whatnot, you would have heard this FE 550, FE 500, FE 555, whatever, right? Brands calling it 555 TMT and all that. So that 555 is the MPa strength, right? That's the tensile strength of the steel. Now, if I were to compromise on 200, 300 MPa on tensile strength, my entire research would take another direction, because the values what I actually got from manual testing would never match with the simulated values that I got from finite element analysis. It would be completely different. Because the material, yes, it is being branded as GFRP. Both are GFRP. But they're worlds apart. Because the tensile strength varies. And when I saw your test results, I mean, I was actually mind blown that someone's doing it this good in India. And I'm glad you're doing it this good in India.
Thank you so much for pointing that out. Our focus right from day one was that when we got into it, that we want to create a world-class product, because our vision is also that we see this as a global brand made in India for the world. So we felt that it should be a product that people should be so comfortable that they can even pick it and export it if they want. And in fact, we are seeing results. Like yesterday, just last week, we exported to Maldives. We're in talks in Sri Lanka, Mauritius, and a lot of other countries as well. So if you take the products, they're all compliant with the ASTM standards. And if you take in the concrete reinforcement, the product, the rebars which have come in, so the BIS standards has come in. So we are one of the very few brands which is 100% kind of compliant. And even in BIS standards, like there are lot of guidelines which are given. Even in those guidelines, we have kind of gone for the best quality material. For example, if you take the resin, so if anybody goes on Wikipedia and does a research on, let's say, your polyester resin or epoxy resin or vinyl ester resin. So epoxy resin is what is always said as having the most mechanical resistance and this thing. So we use epoxy resin in our products. The other aspect is also from a tensile strength point of view. Actually, the BIS codebook only states it to have more than 900 MPa. So we are kind of 100% compliant. Of course, you have seen a test reports that it goes much beyond that as well. But everything is like at par with the BIS standards. And as the thickness varies, the tensile strength does come down. Like for example, if you take a 40 mm or 50 mm, there the BIS standards only says 800 or 900. But in general, the tensile strength more or less is double than that of steel. And as I said, like it is completely at par with the international standards. So that actually brings me to one more facet of this material is that broadly we have spoken about a lot of things. What else would you say is, how is this material actually different from steel? If you can like maybe share a few insights on that.
Well, I can talk about for an hour. The non-corrosive nature of the material is what made it very popular in the construction industry or any industry that it's present in right now, because it's been viewed as a replacement for steel. Now, if I were to talk about it being a replacement, I wouldn't use the exact technical word. I would call it a good alternative for steel. So all our steel code books, whatever we have, right, it's designed and architected just for steel. You can't just take steel out of it and put GFRP and expect it to perform the same way.
That's a very good point, yeah.
We talk about so many advantages that this material has, but there are so many engineering aspects to making these structures, right? So for example, development length is something that is neglected in GFRP structures, especially in rebars. So development length is the length that you put in intersections which provide the strength to the overall connection, the overall joint as we call it. So let's say development length for steel would be somewhere between 4 times the diameter or 6 times the diameter, depending on which code you're following. For GFRP, it would be around 8 to 10 times the diameter. So basically, if this is a column and this is a beam, this extra part, that would be the development length. Now this, we don't just leave it like this, we bend it a little, right? This would be for steel, this would be for GFRP. The length here is increasing. So like that, there are various engineering aspects of GFRP that have to be looked into when designing GFRP structures. Based on this, now, if I were to talk about the advantages, because you can't always keep both the materials and keep comparing and competing between the two. Because GFRP is good in its own way. Steel is good in its own way.
Correct.
You can't just take this there and put this there, and you can't do that mix and match. That being said, GFRP is not ductile. It can be a boon, it can be a bane. GFRP is a non-conductor of electricity and magnetism. Again, boon or a bane. GFRP is rust-free. Rust-free is definitely a boon. It breaks suddenly. Most people would look at that as a negative point. But there are test case scenarios wherein you want something to snap at a particular point. What happens in steel is, steel bends. It bends, it bends, it bends, and then at a particular point it snaps. And the deformation is kept like that only. It does not go back to its original form. Whereas if I were to take a GFRP rod right now, and if I were to bend it, it comes back to its original shape. At the same time, if I were to show it using a steel rod, I can just bend the steel rod and the shape remains the same. Now imagine if there's earthquake in the region and there's some deformation in the structure, right? A little bit of aberration, a little bit of vibration, a little bit of movement. This deformation is going to last in the structure. Now, concrete hanging to this might fall off, might fall on someone whose post-earthquake inspection of any structure is vital. Who a lot of people do not look into and how many structures can you inspect? Okay, the first earthquake, the building stood strong. The second one, it did stand strong again. Third one, fourth one, fifth one. But in all these earthquakes, right, there will be some impact on the building. And it will show in the long run. Maybe on the sixth time, when no one's expecting the building to collapse, it would collapse because of those permanent deformations.
Got it. So as a layman, what I'm understanding is that whenever there's a seismic event, and what you said is very interesting because even though the major earthquakes happen only once in a while, but there are a lot of like minor earthquakes which are happening all the time, like which are like say 4, 5 on the Richter scale or 2, 3 on the scale. So with every such movement, eventually what's happening is that deformation is happening in steel. But in GFRP, because of its nature, where it kind of comes back into the place, it's actually good for the building in a particular way. So that's actually an incredible insight. So in fact, from an earthquake angle, like there are a lot of benefits if this material is exposed, explored is what you would say.
Correct. Again, both the materials, steel, being a structural engineer myself, I don't think so I can never speak bad about steel. Because there's so much of steel that we learn about. Starting from our civil engineering days to even when I was studying about GFRP, I had to use steel as a composite connection. I couldn't use GFRP homogeneously. I had to bring in steel. So there is this ongoing argument. I think anyone can check on the internet, especially regarding earthquake structures, whether GFRP should be used or steel should be used. People say that GFRP lacks the number of plastic hinges required for earthquake structures. And the sudden failure of the material can lead to collapsing of the building. But like you clearly pointed out, my argument is also the same, wherein seismic load is very less. Right? There are small jolts felt everywhere in the world. Right? Other than the fire corner or whatever it's called, the fire line or whatever. There the magnitude of earthquakes is more. In such places, yes, steel might be better because it has more plastic hinges in it. But in those places where there's a little bit of dynamic load, vibrations, a little bit of seismic load, GFRP is definitely better. Because there are no permanent deformations. This bending over the time, it can accumulate and it can lead to catastrophic disasters. In steel that is. At the same time, GFRP failing abruptly also can lead to catastrophic disasters. So, if anyone were to ask me, then is GFRP better or is steel better? Whichever is engineered better to suit a particular case will do the trick.
I think that's a fantastic point. I think, as you very rightly outlined, I think all of us in the industry, we need to really get mature that it is not about X versus Y. It's not about steel versus GFRP.
Correct.
It is about knowing the strengths of a particular material and using it which material is the best. So I think this whole debate itself, which has been going on in the industry, GFRP is coming, it's going to kill the steel industry, or this material is not good. I think it's all like really unfounded. It is, as you very rightly said, it is about what is engineered the best. So take the material which property is the best, use it in your construction, enjoy the benefits rather than kind of like having that comparison. I think this somewhere I think I always feel in our Indian ethos, like we are so used to comparing everything. Even as a child, like we used to be compared to our siblings and everything. So it's like very deep grained in us. I think somewhere we need to like just move out this whole comparison thing and just use the material for what it is. Like,
the envy also comes into play, right?
Yeah.
Now, it's if I'm doing better than you, you're like, why is this man doing better than me? If I'm researching on GFRP, I'm obviously going to advocate for GFRP. If you're doing some research on steel, you're obviously going to advocate about steel. That's when these clashes come. But if you were to sit proper technical people who actually know the field, who actually knows the ins and outs of material science, they wouldn't argue. They would just listen to the advantages and disadvantages. Use this material where it's advantageous, use that material where that material is advantageous. They wouldn't compare the two. They wouldn't say, oh no, use this, use it. They wouldn't do that. Arguments are brought by people who are running the market, the material market, right? Steel is a very big industry.
Correct.
No one would want 1 or 2% of their business slipping away from them. But of course, in today's time, people are hyper aware. Thanks to tech, thanks to social media, thanks to AI. We have big players like Tata getting into manufacturing GFRP as well. And as Nitin Gadkari sir rightly said, that this material is usable in highways and road construction. A lot of new players have gotten into it. Having this said, there are 2-3 issues that I have that comes into play when too many players come into the market. Quality is compromised. I'm using some random GFRP and it fails. So I start branding the material only as bad. And I've seen this in so many cases. I literally suggested to a couple of people, why don't you use this type of mesh? Why don't you use this structure? Why don't you, use a pergola is something that, especially in the coastal region. So there was this one resort. I told them, just try one GFRP pergola. Start with that. What they did was, they installed it. I specifically told them, use steel rivets or whatever. They have used normal nut and bolt and all that. And the grade of steel that was used, they haven't used 8.8 grade bolts. They have used some local bolts. And they have started yanking the thing. And because of that, bearing failure has been seen in the profile. Now, the person who was actually supplying my PhD material, he had some good profiles with him. But he was expensive because he was exporting those materials. These people went and sourced it from some random person. And they got it installed by some random people. If technical people are not looking into this, obviously you're going to have a poorer structure. And that man started cancelling the entire thing. He was supposed to build about 10 to 15 pergolas. He built one and he was quite sad with the outcome. In its true sense, he's right, because the type of manufacturer, the people who were working on it were, not technically trained in that aspect. But I've had other clients who have just loved this product, Like, I do a lot of projects in hilly areas. I do a lot of projects in coastal regions. And every time I suggest this material, they're like, you came in as a blessing into our life. Because when you have kids running around, rusted objects, and every time a kid bruises himself with these rusted objects, they have to go take the kid and get a TT shot. That does not happen with GFRP. Similarly with pets. One more, talking about pets, the biggest problem with some of these poles and light poles and traffic poles, whatever, are bird droppings. They have steel poles, birds sit on it, and they obviously, excrete on them. That leads to rusting. Now, every time it rusts, you have a person going and repainting it. That's a very big issue. Now, rust transmits on the surface. So throughout the surface it spreads. And every time the paint peels off, peeling of paint can cause a hazard. Imagine if paint again is a chemical thing. It can lead to soil pollution. It can lead to, let's say, some, there can be, if I start listing the amount of issues, I think it's a never-ending conversation that we are going to have. So I think there are so many places where this material can be used as a good alternative. I don't want someone to just remove steel from the industry and put this over there. Look where it can be used. Look where steel can be used. Make the best of both worlds.
Absolutely. I 100% agree with you. Even as a brand, we have been very, very cautious about projecting it as like we are replacement for steel or whatever. Like we have always advocated steel was there, is there, will be there. But at the same time, as you rightly said, in certain applications, this makes so much sense. And one of the biggest areas, as you also pointed out, is one is the coastal areas and the hilly areas. It's a no-brainer over there. And especially on the outdoors, wherever there is going to be a lot of rainfall or high moisture content, again, this can be explored. Agriculture is another area where the steel is always in contact into water. And once rusting starts from somewhere, it tends to kind of spread.
Thank God you spoke about agriculture. I would not like to stop your flow. Please continue. But I would love to talk about agriculture. You were saying something. Sorry.
Yeah, please go ahead on that aspect. Like agriculture was just one example I was giving. I was also talking about landscaping is another, whether you are going to water your plants. And when steel will come into contact, rusting will happen. At the same time, if you take, we all have those childhood memories of those TT injections and things like that. So you kind of like really took us back the memory lane. So I think pets is another. Even in agriculture, we are seeing areas where, like say the fruit, for example, it's hanged on like wires, metal wires, and like that rust that can kind of get seeped into the fruit, vegetable. So there are so many. In fact, that this is a very interesting statistic, and I didn't believe it when I first heard it. And anyone not believing is this, like they just need to go on Google and put this term, cost of corrosion on Indian GDP. Just putting these terms, it is 4 to 7% of Indian GDP. That's like crazy amount of money we lose due to corrosion. I could not believe my eyes. And it is only increasing because of global warming. It's becoming hotter and hotter. Secondly, in cities, like the TDS level in the water is so high. That is also leading to corrosion. So corrosion has become such a big issue. At least in areas where it is very critical, I think this can be explored. So definitely agree.
You should talk to someone who's into marine engineering or merchant navy about corrosion. They spend half their time just thinking about corrosion. Even when they sleep, even when they talk. I've had friends who are in the merchant navy and literally their entire family says all this bugger ever talks about is corrosion. There's so much corrosion on the ship, on the dock, on the bay, on whatever. So